Hey, so this is our first video for chapter 3 that has to do with the topic of acceleration or accelerated motion, more commonly known as kinematics is actually what we typically call it in physics when we start to study how accelerated motion is going on. And I kind of put some of these images up here because accelerated motion is something that's really actually a lot more realistic than what we did in the last chapter, which is like constant velocity motion. Constant velocity is very unusual actually in nature. Accelerated motion is almost always what we experience in our daily lives. And it's kind of interesting because with accelerated motion, that's actually what we feel. We have a pretty good instinctive understanding when acceleration happens. You can feel it, like I said, kind of in the seat of your pants. You know when you're doing the things that are considered to be acceleration. But in terms of understanding acceleration in a physics sense, and then the impacts on how that extends out to the interactions between different items, understanding acceleration is actually a really key basic component to like I said, understanding interactions between different types of materials. So I've got, rockets launching, cars moving, all that kind of good stuff. I even put my favorite one of the new Mars lander that's on there, Perseverance, which is actually really super cool the way this thing came down. I don't know if you guys know this or not, but without understanding acceleration and how acceleration worked in a different environment, this thing would have cratered into the ground all by itself, right? So we had to actually be able to bring it in across space, bring it into a different type of an atmosphere that has much less gas to it. It's much less thick than ours. So let it slow down. And then deploy some parachutes, which work differently, obviously, in a Martian atmosphere than ours. And then lower it to a certain position where they dropped off the parachute and then used a sky crane to lower it down to the actual planet surface. Freaking crazy, man. I love that. And by the way, if you haven't looked this up yet, this parachute actually has a hidden code in it. So you have a chance to go take a look up what the code is in Perseverance parachute or the lander's parachute, because this is actually written in binary. It's a cool little message that's in there. Something we should probably all take to heart anyway. So accelerated motion, like I said, it's all around us in a lot of the different things that we do. Let me pull this back up here. Hold on. So with this, sorry, this is my second time recording this video. I tried to record it earlier and it just didn't work very well itself. But anyway, here we go. So what are we going to talk about in this particular chapter, unit, sort of whatever overview of what we got going on? So in this particular video, we're literally just going to do concepts and definitions, kind of talk about what acceleration is, what the basic equation is, that's some of that kind of stuff. In number 2, we're going to talk about actually creating VT graphs and how velocity time graphs are a little bit different, a little bit less clear than position time graphs are. In the third one, we'll talk more about trying to represent velocity and acceleration, again, using vectors. So representing delta V, change in velocity and acceleration, and how we add and subtract vectors is a little bit of a different direction. But that's, again, laying the groundwork to some things that we end up doing with force and energy and some other stuff that's coming up as well. The next video will have to do with interpreting VT graphs. We'll actually show you kind of a variety of them and talk our way through VT graphs and some of the major landmarks that are in there. And then we'll get into the actual kinematics, like the story problems, how do you do the different equations? How do you read and interpret different kinds of story problems and apply some mathematics to it? So that's actually the kinematic stuff. And I'll have an overview video in there, and then there will also be a practice problems video on there, walking you through some of the different types of wording, some of the different types of problems, how you pick an equation, that kind of stuff. And then the last probably 2 videos will be having to do with free fall, maybe 1 or 2. And that's free fall as a special case of accelerated motion, because you're accelerating when you're in free fall. So in terms of what acceleration is, I know you guys know some of this basic stuff that's on there. So acceleration is any change in velocity, right? So you guys are probably familiar with the term accelerate and decelerate. Problem is the word decelerate is not actually a scientific term. So we have to kind of get that one sort of beaten out of our sort of language here for when we're in physics class. We'll use it, but it's not a scientific term. So if we're talking about a change in velocity, right, we got delta V that's going on here. I gotta get my pen, sorry. If we're talking about delta V that's happening, so any sort of change in velocity is a change in acceleration. And because velocity is a vector, it's got magnitude and direction, that means that acceleration also has to be a vector, right? It has to have magnitude and acceleration and direction as well. Keep in mind that this is a little bit sneaky, but there's actually 3 ways to accelerate, 3 ways to change your velocity. One way is increase your speed, right? If you're changing your velocity in the positive direction, then you're accelerating in the typical way that we use that word in everyday language. You can also have negative acceleration, which is not quite the same thing as saying decelerating, but you also know that slowing down is another way to accelerate. It's just the opposite direction. The third way is to remember that when we're talking about velocities, and velocities are being vectors with direction, not only do you change the speed, but if you change directions, you're automatically accelerating. For example, if you just turn a corner, if you're going 10 miles an hour this way and then you're going 10 miles an hour this way, trust me, you feel it when you turn that corner. You know what acceleration feels like. So anyway, speed up, slow down, and change direction. 3 ways to accelerate it. Keep in mind that acceleration is a rate, just like velocity is a rate. It's a rate of a rate, actually. If velocity is the rate of change in position, then acceleration is the rate of change of velocity. It's also a rate squared because it's actually at 2 levels of a rate, right? It's the rate of change of position. I know that sounds kind of weird to say that, but it's doubly. You got 2 different layers removed from position. So position to velocity and then velocity to acceleration. So all of those are things that we know about acceleration. As we're defining it on here, let me do this really quick. In terms of what it is, this is because I'm re-recording it, so I apologize. Let me do this really here. I'm going to clear that out. So what does it mean when we're defining acceleration? So here's our basic equation, right? You know what this particular one is. Acceleration is a change in velocity over time. I wanted to put this up here as the reminder that when we rewrite delta V as VF minus VI, you can still plug that in here. It's still the same thing. However, a lot of students miss that in problems when they're asking about what's the final velocity of something, they miss that it's sort of wrapped up in this delta kind of character. So just be aware that that is what that's referring to. Second thing, is also really common to write this in a slightly different algebraic way. Acceleration equals VF minus VI over delta t. So when we do our rearrangement on this, A delta t is equal to VF minus VI. And then I'm going to move this VI over to the other side. It's commonly written in a way to kind of represent how do you calculate the final velocity of something. So you get A delta t plus VI equals VF. This is our first sort of kinematics equation, which is just a rearrangement of our definition of acceleration, but written in a way to highlight one of the important components. So this is how we would calculate final velocity if you know what the initial velocity was, what the acceleration and the time was. Yeah, by the way, I just want to mention this as well. A lot of times the triangle is left out for t. It's kind of assumed that if you're talking about time, that it's elapsed time, how much time has passed. So sometimes you'll see it as t, and sometimes you'll see it written as triangle t, delta t. They're both the same thing, actually, in this particular case. There is a difference, however, between v and delta v, so we do have to be careful. A lot of times v here means average velocity, and delta v means change in velocity. So this is average, and then this is going to be vf minus vi. So just be a little bit careful with some notation issues. Okay, last thing about acceleration I'll mention, this will be our last slide for today, is that, like I said, that feel for acceleration. You guys know what acceleration is because you've experienced it before. Truly, our brains are wired in to detect acceleration. We have built-in accelerometers, actually in our ears of all places. We can talk about the structure of your ears, that determine position and movement and all that kind of stuff. But we really are sensitive to acceleration, changing velocities. If you guys have ever been on like a plane or on a coach bus, something along those lines, it's going, cruising along at its cruising velocity, and it's not changing its motion at all, you can almost forget that you're moving, right? But as soon as it starts to change its motion, go over a bump, go around a corner, or like in a plane, start to descend, you can tell right away. You feel it in the pit of your stomach, you feel it up in your head, you kind of like wake up and look around and go like, what was that? But it's that change in motion that really shows a lot of information to our brains. In fact, what it does is it creates force and that appearance, that feeling of energy, I guess, in there somehow. Furthermore, I want to say this as well, and it's kind of the joke that's on the screen there. It's not the fall that kills you. With acceleration and velocity, nobody's ever died from high speed. Not at all. No one's ever actually died from jumping out of an airplane. What you die from It's hitting the ground. And it's not even just hitting the ground, right? It's hitting the ground at a certain rate. If you hit the ground without a parachute, you're flat. You hit the ground with a parachute, if all goes well, and you're fine. You can walk away from it because what you're doing is changing your rate of acceleration. You're changing how quickly or how slowly you're going from terminal velocity to zero. And that's really the key point that's on this. So when you're doing things like roller coasters, like this one part here, the reason why roller coasters and amusement park rides work is because you're always accelerating. A ride with no acceleration is super boring. That's called being in a car. But with these things, roller coasters, you're always speeding up, slowing down, or changing direction. 100% acceleration in any good amusement park ride. Similarly, our friend here, our skydiving friend, he is probably currently not accelerating. He's probably at terminal velocity, which means he's going constant speed because his wind resistance, his air resistance is combating his acceleration due to gravity. So he actually doesn't even feel like he's accelerating. That's why skydivers can do the tricks and things that they do, because it's almost like holding still in any fluid, like in water or something along those lines. But it's the change in motion that gets you, like this poor guy here getting hit in the face with the soccer ball. Man, that soccer ball is decelerating rapidly on his face. Same thing, my little wiener dog friend here didn't expect that change in acceleration due to the sand. And then my jokingly one friend up here, fail videos. Fail videos are all about this, right? This is exactly what fail videos are built on, is humorous changes in acceleration or incorrect expectations of what your acceleration rate is. Our friend here leaping off that first-story building, he may or may not get hurt. It kind of depends on his deceleration, on his rate of change of velocity. If he hits that water, he could be just fine. You could just jump right on in there. If he belly flops in there, man, his acceleration is going to be a little bit faster than he was expecting, and that's going to hurt. Hits this concrete right here. Wow, that's one heck of a rate of acceleration and not in the good direction, right? So again, acceleration is really about that change in velocity. It's about the feel of change in velocity, and being able to discuss it, quantify it, is actually really fundamental to understanding a lot of the interactions that happen in physics. Constant velocity, super boring. Changing velocity now, that's where the fun happens. All right, I'll see you guys in the next one. Have a good one. Bye.